Hello and welcome back to Calculus 1 Saturday edition 3.10 on derivatives of inverse trig functions. A little bit of the review on inverse trig functions and what they mean, and then we're just going to list the formulas, literally do two examples maybe if so, and move on with our lives. It's a very short section. What is the meaning of the inverse trig function? Well, if you have a trigonometric function y equal sine x, then the y is the ratio of a number as a over b, and x is some kind of angle. So if you say sine of 60 degrees is equal to 1/2, you can also do that in radians. 60 degrees is pi over 3. 1/2. So this one is either given in radian measure or a degree measure, and that's an angle. And then over here you have a number. So that's the deal how this goes. So now, if I have an inverse function, remember what the inverse does. Swaps domain with the range. So in this case, x equals sine y when you swap it. And then you apply inverse, what we call inverse sine, on both sides. And you get that your inverse function of x is inverse sine of x. So in this case, inverse sine will take in 1/2 as the input and spit out your angle as a result. Technically the undo button, right? So you go forward with sine. Let's put a, I don't know, tangent example. Tangent of 30 degrees is √3 over 3, which means that the inverse tangent of √3 over 3 is 30 degrees. So that's your life between these, right? Now some functions, right, in calculus will be used to model primarily inverse tangent. So we're going to have a lot of derivatives of inverse tangent all over the place, sometimes inverse sine. And we want to pile up all of this, right? We want to pile up all of the derivative formulas for inverse trig. So here are the derivative formulas. They can be derived using, obviously, implicit differentiation and ideas of, the way you swap this, you take the derivative and you go through. If you are interested, one of them or two of them are derived in the book. You can practice. Again, this is mainly for honors course. We have the vanilla Calc1 here, so we do not go into those derivations and proofs. But they're not complicated. Here's the derivative of inverse sine of x, and that one is 1 over square root of 1 minus x squared. And the derivative of inverse tangent of x is 1 over 1 plus x squared. So these two formulas show up a lot. Well, primarily tangent. The other four, not so much. They obviously are going to be in the homework section for this chapter, but that's it. Here we have 1 over absolute x square root of x squared minus 1. Now, the coolest part about these is that the inverse trig functions of the other three will have the same formulas, just with the minuses in front. So d dx of cosine inverse of x is the same formula with just a -1 on top. So they're very easy to memorize. But
and
still,
that secant, that's absolute value. Those obviously, those aren't ones, right?
Yes, that's absolute value.
Okay.
Well, I should be writing 1 like we do it in Europe, but then people over here say, is that a 7? And then I have to say, no, this is a 7. So proper way to write 17 would be this. But then in US, they told me that I should be doing this. And then now I have to talk to you, right? Right? What's absolute value and what's 1? If we were all writing the numbers this way, then we would not have that issue. But such is life. All right, so let's go with the rest. The cotangent -1 of x is going to be the same. It's just a -1 on top. And then this one, again, the same. Just put the -1. So cosecant inverse of x is the same formula with just a -1 on top. You have your absolute x. Square root of x squared -1. This is it. Now we can enhance these formulas instead of x's to use a function which will introduce the chain rule. And then you just worry about product rules and quotient rules, and when they show up mixed with other things. So the most important of all 5 is tangent. The next one would be sine, inverse sine. And then the other 4, I don't recall I ever seeing them outside of this section, right? The homework for this section. I don't recall seeing them in any of the problems ever, in any of the Calculus1s. So, whatever. But let's take a look at this inverse tangent business. So what would be the inverse tangent of a function, right? So if I have a tangent inverse of not x, but f of x, right? The formula would change like this. So I hope you can let's put the blue. Do we see that it's the same formula and you just have that chain rule of f prime? So you still have 1 plus technically x squared is f squared, and you just have that prime f prime on in the numerator. So you can convert all of those 6 formulas into the general case. Like if you want to, let's say, work on the secant formula. So I'm just going to box this one. And the reason why I'm singling out this tangent is because it shows up a lot later on in your future coursework. So I'm going to single that one out and clearly discriminate against the others. But then I'm also going to say, what if we had the derivative of secant inverse of f of x for whatever bizarre reason, right? Then it would follow the same rules. You would have, instead of absolute x, absolute f of x. Then you would have your square root of f squared -1, and the top would have the f prime. It's a pattern, right? All x's are replaced with f of x because that's the function composition. And then everything is multiplied by the derivative of f, which is the basic chain rule. So now every formula in the future for whatever, in Calc 2 you will learn hyperbolic functions, and they have 6 functions and then 6 inverse hyperbolic functions. They all follow the same rules because the chain rule is the rule on a function as a concept, not on a particular function, like let's say only exponential and only logarithmic. No, it works on all of them. The chain rule works for all functions equally, the ones that you have learned so far and the ones that you will learn and the ones you will never learn, right? So there are thousands of functions out there. You always fix your formula with the chain rule and you replace every x with this. The same thing you did for the derivative of square root of f of x, right? If you have a square root of f of x like this, that was f prime divided by 2 root f, right? And your original problem was just 2 root x. You replace x with f of x, and then you put the derivative on top, because every chain rule is always times f prime of x, right? Well, it was a g in our case, in a formula, but whatever. Cool. And now the way you use these formulas is, I don't know, second grade thing. What is the derivative of secant inverse of, let's say, e to the x? I don't care. You go and you say, okay, I have e to the x here, then the square root of e to the 2x minus 1, and the derivative of e to the x is e to the x. These puppies will cancel, and I just have 1 over the square root of e to the 2x minus 1. Done. That's literally what it takes. You know that your f of x is e to the x. Take that e to the x, Control C, Control V, Control C, Control V, square it. Take the derivative and plug it. There shouldn't be thinking anywhere in this process. You are literally plugging in f of x and f prime of x where they belong in the formula and just simplify algebra at the end. So there is nothing special about this. Let's take a look at one more example. So let's say you want to find the derivative of cosine inverse of xy equals to 16. We use 16 a lot today. How about 9? You say, oh, this is implicit differentiation. I also have a product rule. I also have inverse cosine. Ugh, right? Just gonna plow through all of this. The derivative of cosine is given as negative, right? So we have a negative 1 divided by, and now this is 1 minus, and instead of writing x squared, you have xy squared, because that is the chain rule. Now, times the derivative of this, and that would be a product rule. So, copy the first, derivative of the second, plus copy the second, derivative of the first. You are done with your inverse cosine. Here is the inverse cosine, and here is that f prime that should be going on top over here. We put it as a chain next to it, right? Because we had to do that. Equal to 0. And now you just follow the rules to write this the way you want it. Now, when you have implicit differentiation and you have a constant on this side, you should be doing the little woohoo, right? Because if you multiply the entire equation by the square root of 1 minus xy squared, if you multiply the entire equation by this, it will just cancel here, and this multiplied into 0 still stays a 0. So the entire problem now actually is just, you can also multiply by a negative of that, because that will also kill that negative there. So your problem is just x dy dx plus y equals 0, from where dy dx is negative y over x. Cool, huh? So these are some of the things, and it literally just, you're replacing the values. You are replacing the values, and we just added more with this example. You can go back and watch this example again, and see that you have the inverse cosine. Then within that one is a product rule, which is here, which at the same time is your f prime, right? Then that f prime had the chain rule here because we had the derivative of y. So it's like a triple deal at once. And then a little bit of algebra here to because it's equal to 0, right? We can kill that kills the denominator. We can also kill the negative up there, so the whole thing drops. And you just have this, just because this is 0. If this was 9x over here or something, then this beautiful simplification would not go that well. It's just because it was a constant and it was 0, you could have used something like this to simplify. I hope you're not disappointed. That's your inverse trig functions. And please, please, please make sure, right, that that you really know these two, primarily inverse tangent, and you know, how about I write this, because other courses are coming up, and that one should be around. That's it. It's always like 10-15 minutes for this. Not a big deal. Plug everything in the formula and done. Questions, concerns, anything?
Could you scroll down for a little to that problem?
Scroll down a little. There you go.
To the problem, like you just did.
Yeah, I know.
Could you, I guess, to get more practice with the logarithmic like solving, is there a way you could do it? Like, could you show us how to solve this using logs, or can you?
Yeah, well, the logs would not work here because you do not have, you only have one term, right? The log breaks
right.
multiple terms. So if
XY is one term.
If I had x squared over here, then I can kick in with the logarithmic differentiation, because I would have log of this plus log of that, and then it would work, right?
Right.
Right now I only have one thing, so logarithmic differentiation unfortunately doesn't kick in, right? The nail is way too small for the 40-pound sledgehammer in this case. All right, you're technically, you know, hammering the needle.
So you should only really use it if you have two terms. You can just forget it if you only have one term.
Yes.
Okay.
That was a good question. Nice.
Hey, Professor?
Yes.
Can you just give an overview of what chapters exam 2 is going to be on? Is it going to be all of chapter 3? Oh, that's it?
Why, disappointed? Okay, we can add stuff. Let's see, what else can we add? Since I don't want to disappoint you, man. You sound so disappointed.
Let's add chapter 6 along with it. How about that?
Oh, what about 1, 2, 3?
Ooh, see? Now we have a good proposition on the table. Have a cumulative exam. Chapters 1, 2, and 3. There is just so much material in chapter 3 that without adding anything else, right? Remember, your limits are still the part of that, because what was 3.1? Figuring derivatives using limits, right? Right. So, are you going to have a limit problem on your exam 2? Definitely. It will just say, compute the derivative using the limit definition. You're still doing the limits there, right? So, the limits are not going away. The only concept that you possibly dodge on the second exam from what we did so far is continuity. Like, that's the only thing that you could possibly dodge on exam 2, you know, going through all of the pre-calc we did, all of the trig we did, all of the limits we did. The asymptotes are still with us in terms of, I mean, horizontal and vertical lines, because now you have horizontal and vertical tangency, right? So technically, you know, that stuff is still around. Yeah, and it keeps building up. We'll go into chapter 4. We're going to use all of chapter 3, and then there is going to be 4.7 or 4.8. L'Hopital rule, which will be the section on limits. But those limits are 4.7. Limits using derivatives. So you really don't get to escape any of the stuff from before, and if you have issues with limits, yeah, you're gonna miss one problem at least on exam 2, You're gonna miss at least 2 or 3 problems on exam 3 for L'Hopital's rule. If you don't understand limits, you can't do L'Hopital rule because that's all limits. So yeah, if you have issues with limits, please stop by my office hours, see what's wrong. Let's talk about it. Let's figure it out. I'm gonna stop the stream. Just gonna say bye to YouTube people, right? And I'll be switching soon to my office hours so you can join me.